Welcome to Unit 1, Lesson 1, Part 2. This comes from Pearson, copyright 2009, Algebra 1, Lesson 3.8, Finding and Estimating Square Roots. The objective today is I will be able to estimate the value of a square root of non-perfect squares. I'm Mr. Pilarski and I'm your teacher this year. Let's get this math video started. On this side we're going to be talking about finding square roots. The key thing to remember is that the opposite of squaring a number is taking the square root. If you can remember that, much like addition and subtraction are opposites, and multiplication and division are opposites, the opposite of squaring a number is taking the square root. So we can see over here, 4 squared is equal to 16, and negative 4 squared is equal to 16. So the square root of 16 is 4, and the square root of 16 is also negative 4. We're going to talk about this having two answers in a little bit. The very algebraic definition taken from Prentice Hall's Algebra 1, page 176. The number a is a square root of b if a squared is equal to b. Here we're defining square root. Here's a numerical example again. 4 squared is equal to 16 and negative 4 squared is equal to 16. So 4 and negative 4 are square roots of 16. This very well could be a core objective in class. Opposite of squaring a number is taking the square root. And in fact, we could probably improve this by putting the word the in there. Little language arts there. Reading and revising what you wrote. The opposite of squaring a number is taking the square root. So you're going to probably want to say that a few times because that's an important fact. Here we're still finding square roots. We're going to talk about the symbols and some key vocabulary that you need to understand when working with square roots. A radical symbol indicates a square root. The expression the square root of 16 means the positive or principal square root of 16. The expression negative square root of 16 means the negative square root of 16. The expression under the radical sign is a radicand. Again, if you want, you could have done that as a reading activity, fill in the blank, then watch the video to see if you got the answers right. Let's move on to finding some square roots in example 1t. Here we are actually finding square roots in example 1t. We're told to simplify each expression. Well, the first expression in A is the square root of 25. Now remember, taking the square root of a number is the opposite of squaring a number. So you got to ask yourself, what number squared gives me 25? And since there's no sign out here, we want the positive principal or principal square root. And the number squared that gives 25 is 5. Okay, and you might even put a reason down here because 5 squared is equal to 25. Here in part B, we want both the positive and negative square root, so we know our answer is going to be positive and negative. In the numerator, we ask ourselves, what's number squared gives me 9, and of course that's 3. And what number squared gives me 25, and you should know from part A that that would be 5. And that's because 3 squared gives us 9, and 5 squared gives us 25. In part C, what we're looking for is the negative square root. So we know our final answer is going to be negative. And what number squared gives us 64? That would be 8. So our final answer here is negative 8, or the opposite of 8. Example D, we can't do right now. You'll be able to do that either later in Algebra 1 or definitely in Algebra 2, where we have the square root of a negative number. We can't do that right now, so just put a little X right there. Just know that. And in part E, we want the positive or the principal square root. And to do that, we take the square root of 1, which of course is 1, and the square root of 16, which is 4. So in that case, the answer simplifies to 1/4. So far, what we've seen is that all of these numbers, except for d, which we could take the square root of 49, which would be 7, but since it's negative, we don't know how to handle that yet. You'll learn that in Algebra 2. All of these numbers you were able to take the square root of, and we're going to learn a little bit about that later in the lesson, perfect square numbers. Finding square roots, rational and irrational numbers. Take 1. Action. Some square roots are rational numbers and some square roots are irrational numbers. Now, we learned about those in a previous lesson, where rational numbers are any numbers that can be expressed as a fraction in the form a over b. And irrational numbers are numbers that cannot be expressed as a fraction, that don't give us a repeating decimal number or a terminating decimal number. Here are some examples. A rational number example would be the square root of 100, because 10 squared is 100. Here, using your calculator or some basic math skills, the square root of 0.36 is 0.6, and that would be the positive negative square root. And the reason that this is considered as a rational number is it can be written as 6/10 and then reduced to 3/5. Here, the square root of 16 is 4, and the square root of 121 is 11. Again, expressed as a rational number, as a fraction a over b. Here are two examples of irrational numbers. The square root of 10. There is no whole number that we can square to get 10, and the resulting number is irrational. There's no identifiable repeating pattern. And the same with the square root of 1 over 7. There's no number, whole number, or rational number that we can square to get 1 over 7. And the resulting number is an irrational number because there's no identifiable pattern, or it doesn't terminate. It goes on forever. And this is taken from Prentice Hall Algebra 1, copyright 2009, on page 177 of our textbooks. Finding square roots, example 2t. Here we're told to tell whether each expression is rational or irrational. Remember, rational is in the form a over b, a fraction, and irrational is a number that can't be. So here, part A, the positive and negative square root of 144, well, that's going to be rational. And the reason that's rational is we can rewrite or take the square root of 144. What number squared is 144? Well, that's 12. So since we have positive or negative 12, and that can be written as positive or negative 12 over 1. It can be written as a rational number or a fraction, a over b. In part B, that's irrational. And the reason that's irrational, in the numerator, we can find a number that squares to give us 1. That would be 1. But in the denominator, there's no number that gives us whole number that gives us 5 squares. So since we can't take the square root of the denominator, this number ends up being irrational. Now, a lot of students look at example C and think, oh, that's going to be irrational because it's a decimal. But if we convert that decimal into an improper fraction, remember, let's take a look at this. This is the negative square root, and it's 6.25. Now that'd be 6 and, not 2, but 6. Six and 25 hundredths. And that fraction, 25 hundredths, can actually be reduced to 1/4. So that'd be the negative square root of 6 1/4. And then we change that mixed number to an improper fraction, or as a rational number. So that'd be the negative square root of, and that's 4 times 6 is 24. And 24 plus 1 is 25. That'd be 25 over 4. And then we can take, and that's going to be the negative or the opposite of whatever we get. And since we can take the square root of 25, which gives us 5, and the square root of 4, which gives us 2, since we can express it as a rational number, this thing is going to be rational. Similar to C, D is going to be rational also. And the reason is we can simplify the square root of 1 to 1, and the square root of 9 to 3, and 1/3 is a rational number. Therefore, This answer is rational. And since there's no whole number that we can square to get 7, this thing is going to be irrational. Without a calculator, the best we can do is estimate square roots. And here we're going to have some information on estimating and using square roots. The squares of integers are called perfect squares. So here we have consecutive integers 1, 2, 3, 4, 5, 6. Their perfect squares are 1, 4, 9, 16, 25, 36. You can estimate square roots by using these perfect squares. Now, what I'm going to want you to do is list these things out and learn these perfect squares for the consecutive integers 1 through 20. It's going to make life easier and quicker if you know those. In fact, if you remember back, I mentioned these perfect square numbers as I was doing the first couple examples, and having a knowledge of or memorizing these numbers is going to make your life easier and quicker when it comes to doing math assignments in class and outside of class. In example 3T, before we get started to it, I want to point out that this number here might look like 28.34, might be 28.34 in the handout that you're using. Just scratch it out, make it 8.34. I just want to point that out before we get started. Between what two consecutive integers is the square root of 8.34? Well, to do this, we have to think about the perfect square numbers. The perfect square numbers being 1, 4, 9, 16, 25, and so on. 8.34 is between 4 and 9. So the square root of 8.34 is going to be between the square root of 4 and the square root of 9. When we take the square root of those numbers, that gives us 2 and 3. So we know now that the square root of 8.34 is going to be somewhere between 2 and 3. Now that's kind of how our textbook, Pearson Algebra 1, copyright 2009, shows this example. I like to take it a little step further here. Without a calculator, estimate to the nearest tenth the value of the square root of 8.34. Now when I attempt to do that, I got to figure out how close it is to 4 and 9. Now, looking at the answers here, 2.5, 2.7, 2.9, and 3.1, right away I can eliminate I can eliminate 3.1 because that's greater than the square root of 9, which is 3. Now, 8.34, if you think about this as a number line, 8.34 is very close to 9. Okay, so the square root of 8.34 is going to be very close to 3, and the closest we can get to 3 out of all our numbers is C. So I'm going to say here, venture to guess that if we round it to the nearest tenth, the square root of 9 is going to be 2.9. And in fact, if you check that with your calculator, you'll find that to be right. And since the square root of 8.34 is so close to 9, of these three answers, the best answer is the one that's going to be closest to 3. Here in example 4T, I'm actually going to cut away, show you how to use a calculator to find the square root of 28.34. In example 4T, we need to find the square root of 28.34 to the nearest hundredth. We can use a calculator to do that easiestly. In fact, getting to the nearest hundredth without a calculator, I don't think that it's impossible, but that's why we have calculators. So let's take a look at it. Here we're using a TI-83 Plus, and to use that calculator we need to access the second function key. You can see how it's flashing an arrow if you have a calculator like this. Above the x squared key is the square root key. I don't know if you can see that or not. Let me see if I can focus in on that. No, not too well. But above the square key is the square root key. You hit that. On the screen you can see the square root symbol with a parenthesis. Then you enter the number you need to enter, 28.34. You can close the parenthesis. In this case you don't necessarily have to. And then to get the answer to the nearest tenth, you hit enter.
or actually it's near hundredths, so that'd be 2 decimal places. So that'd be that 2 there. And the 3 to the right of the 2 tells us to keep the 2 the same in our rules of rounding. So the final answer here would be 5 and 32 hundredths, and that'd be approximately, not exactly.
Example 5t, we're actually using square roots here. Suppose a rectangular field has a length 3 times its width, x. The formula d is equal to the square root of x squared plus the quantity 3x squared gives the distance of the diagonal of the rectangle. Find the distance of the diagonal across the field if x is equal to 8 feet. Okay, so let's take a look at this. What this amounts to is a substitute and solve problem. What we'll do first is write down what we are given, the equation d is equal to the square root of x squared plus the quantity 3x squared. And to do this, we substitute 8 in for x and then we simplify. This takes quite a few steps. You could probably use a calculator, but it's kind of cool to be able to simplify these things. So in for x goes 8. So 8 squared plus the quantity 3 times 8, all squared. And remember, we're going to take the square root of that thing. So when we do this, 8 squared, we start simplifying underneath the radical symbol. 8 squared is 64. And then we have to add that to 3 times 8 before the exponent because it's in parentheses. So that'll give us 24 squared. So right now we have a little more math to do. And that math being 24 squared. You can use a calculator, or if you memorized your squares through 25, which is probably a good idea, but 24 squared is 576, so that'll give us underneath the radical 64 plus 576. And when we simplify that further, when we add underneath the radicand, that gives us 640, 640. So now we could plug that into our calculator. Remember, using a TI-83 or even a TI-94, probably second function key square root 640, and rounding that to the nearest tenth, which it doesn't tell us to do, but I'm going to do, it's going to give us 25.3 feet. So from here to here, I just use a calculator for that. It's essential that when you simplify expressions underneath radicals that you follow the order of operations. Mostly here where I had to multiply 3 times 8 before I squared the number.